I want to share with you this phenomenon that every structure can be modeled as mass spring damper system, and you can see that what is the bandwidth of that structure. Like, is it a low pass filter? Does it behave like a high pass filter or a band pass filter? Filter is a terminology which we can use that it filters out certain frequency components that it does not uh, vibrate at a certain amplitude. How would you define the amplitude? So this is a frequency range starting from 0 to a certain value, keep going, and you see that it is very low. The magnitude, this is on the y-axis, the magnitude, and if it is starting certain magnitude, the dB value. So this is a very helpful way to see. I would suggest you when you go home to see the practice problem which I share with you. The I think I made this yes, like this one. So if you give a command Bode transfer function, for example, I gave this expression as T letter and showed you that this is the frequency response from the Bode plot, and then you have to select in since it is -60, so you have to add 3 dB to go below the 3 dB is the like it is the value where the lower than that value is not required for our bandwidth. We should keep the magnitude above this value. And where is the mass resonating or the system resonating? So if you see this example is telling you that it resonates in this region. So starting maybe from 95, and this can be guessed like a 3,800 something radians per second. So now I'm gonna explain you the bandwidth concept. So as you know that this is the magnitude formula. X is the output response divided by the input force. This is the transfer function. Um, and the magnitude we call it as magnitude ratio, and you have to take the um, log for the. So how would you take the in order to make this k like this as an fx force, so you have to do like this. K is multiplied by this cross multiply, because force divided by the applied force, output force divided by the applied force is considered as the also the magnitude ratio in terms of the force dimensionless quantity. And then we can take the 20 log of this value and then plot it. So if you plot it, then you can get this answer here. So it starts from 0 dB, and you see 0 dB means like a log to the 1, which is 0. So 20 log of 1. Why is it 1 if you consider this as 1 with zeta equals to 0 in over here, and then you can change the value of zeta and starting frequency r equals to omega over omega n, where omega can be considered as 0. So it's like a 0.1 is almost very close to the 0. And what happens when the forcing frequency equal to the resonance, you will see a largest peak. And this peak changes with the zeta value. If you have zeta very small, like very small damping coefficient, the peak is very large. If you keep on increasing the damping coefficient, the peak goes on decreasing. And here you have the a very high value of zeta, and then it goes down negative 40 dB per decade. So this is the also known as the Bode plot. This is the magnitude plot. And how would you draw the phase plot? I believe I showed you this phase plot here in the previous video. So you will see the deflection from a certain angle to the new angle, that if you see 90-degree phase change, then it's a point where the resonance is occurring. As you can see, this is a since this is a second order differential equation, so therefore we have uh, 90 dB per decade. So the total phase change is 180 degree. So underdamped model can be written like omega n squared or s squared plus 2 zeta omega n plus omega n squared. Now this concept is leading us to the new concept of resonance and the bandwidth. So what is the bandwidth? As I mentioned, it is the frequency range where the amplitude is uh, recommended. Like if it goes below a certain value, like MP divided by square root 2, if the magnitude is below that value, then we neglect those ranges. Like over here, you see, we will not consider this. Only it filters out. So the left out filter is a band pass filter. It only allows the frequency range in that band where the magnitude is acceptable. I will just eliminate these. uh, Suppose this is a system where there is no zeta. So I want to jump to the beating frequency. This is equation 4.2-2. So, and what is beating? Let me show you if the forcing frequency. Let me show you the concept of beating. Like if the forcing frequency is very close to omega n, they are not that far, so then the system behaves like um I would say constructive interference and then destructive and then constructive interference then destructive. So you see in acoustics or in sound waves, when you have two resonances of where like 400 hertz and one instrument is playing at 380 hertz, so you will hear some kind of beating phenomena in which the you will see sudden destructive interference where there is no noise or no music or no sound, and then there is a sudden constructive interference. This happens. So what is that beating phenomena? So let me show you this graph here. So example of beating when the forcing frequency is very close to the natural frequency. So you see this is the the period of beating frequency is like a one, it acts like a sine wave. Sine wave, the period is 2 pi, but the beating is half of the sine wave period, because in one sine wave the it happens twice. So the beating period can be found from this plot. The theory behind it you can read it at home, but I just want to show you. You will not be asked to derive the theory formula, but you may see the practice problems to find out the uh, frequency of the signal. So as this is the formula here, and the beat period is given in this equation, and the vibration period is over here. So if I write down the complete equation for the displacement, I did not add this one, so I want to add another equation here. This is the vibration period, uh, and this is the beating period. So these are the vibrations, okay? The period of this vibration is like 2 pi over what, imagine this is omega. 2 pi omega is omega plus omega n over 2. So this 2 goes in the numerator. So the vibration period is omega 4 pi over omega plus omega n. And for this one, it is the same thing, but I'll tell you why is it. So this one, the vibration, the period is, imagine this is omega omega minus omega n over 2. This goes to, so it is 4 pi over omega minus omega n. But you see, beating happens twice in one cycle of sine pi, so it is, so the period is 1/2. I would say this is 2. So that's why we have a 2 pi over this frequency period. So now, what is the bandwidth? As I mentioned, that the band in which the magnitude is acceptable. Suppose it's a mass spring damper system, and it has been given harmonics sinusoidally, and you see you already found this magnitude ratio x over f naught. So if you will see the value of r, if the peak, this is mp, right? This is mp, but this, if this general amplitude magnitude ratio is equal to mp over square root 2, then you will find the r value, and that r value is, it tells us that these are the frequency ranges. So let me show you that if you do the math, you will get this answer for the r value. We will solve one problem about this in just now. So let's see, this is, so the main idea that this R value, if you give this forcing frequency with this R value given in this formula, then it will, the the frequency have this bandwidth. The amplitude ratio would be MP over square root 2 at that. So this formula is, it will help you to find out the proper magnitude, acceptable range of the magnitude. So I'm going to show you a few cases. The first case I'm going to show you is this case, this is the magnitude ratio, and you can easily see that suppose this is dB over here, so this is 5. So maybe if you subtract 3, 1, 2, 3, so maybe this is the range. So this range is the also known as a band pass filter because it allows certain frequency at which we have the required value of the amplitude ratio. Another example I'm going to show you is, so this one is, so this case is low pass filter. So maybe you can see, I believe it is 0.707. So you see, if it goes below this, so this is not acceptable region. So it allows the frequency, we call this as a low frequency contents are, uh, they provide certain amplitude of the mass. This is mass spring damper system. Okay, if we excite this, and then it has certain value of zeta. Now looking at this one, what do you suggest your professor? Is it allowing the high frequency contents or low frequency contents, or the band pass frequency contents? What do you suggest looking at the magnitude response?
High.
Yes, good job. So this is allowing us that the it can pass, like if this is a, it keeps on growing. By the way, it keeps on growing. So if the 1 over square root 2 is 0.707, correct? So if we see this is about 1, so you see from here onward, this is going towards infinity. So this is also known as the high pass filter. So what it happens, so if I pick this mass spring damper system, so imagine I'm giving a very high frequency to this mass spring damper system, then at with the high pass filter, you will see the magnitude will be in our required range, that is not less than mp over square root 2. If it is mp over square root 2, that portion is neglected. You see my point? So let's see one more case. You can tell your professor that in this case, is it a high pass filter, low pass filter, single pass band pass filter, or a double band pass filter? What do you suggest your professor looking at the figure?
Want to be low?
Yeah, it is. Look, it is having two peaks, MP1, MP2. So what I would do, I would take the minimum MP and see less than, like if I go 3 dB below. So I'm having two band pass filters. Sometimes you have the two band pass regions in the system. So you can easily see, like this is a single band pass filter, this is a low pass filter, and this is a high pass filter. So this one is a double bandwidth uh, pass filter. This is also, this can be another case. So the main takeaway from this section is that when you have a transfer function, you can plot it in MATLAB. Type in Bode. I can probably, I have shared with you the videos, so you can do some, and maybe you can do some homework regarding this. And sometimes we Consider the band pass filter or the low pass filter starting from 0 frequency. So in that case, if it is starting from 0, so at 0 frequency, you can see that damping coefficient goes to um, like spring this 0 over here, and we don't have any zeta on the right hand side. In that case, if you find out the solution of this, at what is the R damping ratio. So this is a special case that if you want to start the lower frequency from 0, then there can be a possibility that you plug in upper as a range and 0 as a lower value. But the most of the time, I will suggest you will use this formula to find out the frequency ratio. Now, in regard to the bandwidth, you will see the when you design a vibrometer or accelerometers, so what is the range in which the you can find out the displacement, which is known as a vibrometer. So let me write down this word, instrument design for vibrometer and accelerometers. So how would you define the frequency range such that it behaves like a vibrometer, or how would you define the R value? So I would say R is the frequency range in which it responds. Uh, the response is like a vibrometer or displacement. So here, this is the voltage. Voltage is K times Z. Suppose this Z is the difference between the mass as well as the platform. This platform is vibrating. So find out if I find out the mathematical equation or the free body, let's start from the free body diagram of this mass. So this mass is having the spring here and the damper here, and this the base is attached with this which is also moving at a certain amplitude, and the mass itself is also, it is moving at a certain amplitude, and the total instrument is, this is some kind of potentiometer where you this is the voltage is directly proportional to the displacement. So how would you model this one mathematically? Look, if you take the free body diagram, if the mass moves downward, the dampers and the spring forces will be like this: negative k x minus y, negative c x dot minus y dot. Negative means like it is opposing the motion constantly. So all the forces, they are equal to mass times acceleration, and I will use this as, this is a spring force, this is a damper force, this is equal to mass times acceleration. So when you see, let me show you one thing there. And if you plug in, look over here, Z is what? Z is the difference of the this mass displacement and as a, so what is Z? If Z equals to x minus y, What is z dot? X dot minus y dot. What is z double dot? Z double dot is x double dot minus y double dot. So I can also write down x double dot in terms of z, so z double dot plus y double dot. So if I replace this x double dot by this one, can I write down like this mz double dot plus my double dot. So if I rearrange this, and this I can replace by z, and this I can replace by z dot. So I can rewrite the whole equation in terms of z on the left hand side. So m z double dot, this goes to the right hand side, this goes to the left hand side. This is like become c z dot plus kz, and the the other side is my double dot. So this is the same equation which has been written in our book. So if I show you this cut and paste of the equation. Now, what is the magnitude ratio? The magnitude ratio is the output over input, output displacement over input displacement. So if you do the math here, so output is z and input is y. So I can write down the magnitude ratio. So this is how you will write down the magnitude ratio with different value of zeta. So let me show you the response. So what it is telling us that usually the response around like if, so if r is greater than or equal to 3, then this instrument behaves like a vibrometer. And I can show you this why is this so. So let me show you if this response is equal to 3. To make it vibrometer, the plot shows that the device natural frequency must be selected so that omega is very, very large than omega n, where omega is a forcing or oscillation frequency of the displacement measured. So magnitude is approximately equal to 1 over here, and a very, very high value, which is about like if you consider this as grade R, which is the frequency ratio greater or equal to 3, then it behaves like a vibrometer. So this Z, as I mentioned, the voltage is directly proportional to the Z. So it is reading the displacement of this instrument, which is our vibrometer. The purpose of vibrometer is to find the displacement. Okay, the purpose of accelerometer is to find the acceleration of any structure which is vibrating. We do have in our lab, we do have accelerometers. If you want to do some project, you are welcome to do that in our lab. And I have done some vibrometer. My whole PhD thesis about was about the vibrometer from the human skeletal muscles. They vibrate when you do some exercise. So the next thing is, if you can see the at low frequency, like frequency ratio, the instrument behaves like an accelerometer. So if R is less than or equal to zero point 0.5, then it behaves like an accelerometer. So omega frequency, oscillating frequency is um, very, very small. So let me show you why is it so. So over here, so an accelerometer, if omega n is very large, then the forcing frequency it behaves like a accelerometer, and the transfer function can be written as minus s square over omega n square. This term goes to zero, this term goes to zero, because anything like infinity is zero. So imagine this omega n is very, very large. So this is but one will still there remain over here, 0 plus 0 plus 1, and you don't need to make it 0 because it's a numerator, otherwise it's a trivial solution. So it is vibrating, therefore we have to consider the numerator. So how about this? So you're left with t equals to, so what is t equal to? Z over y, which is equal to minus s square over omega n square. Approximately, I would say approximately, because we are assuming that omega n is very, very high. So if you do the math, we are interested in z. What is z equals to? Minus 1 over omega n square s square y of s. And this is also, if we consider this one, is also equal to y double dot, because s square means double derivative. So what is double dot means? It's acceleration. One dot is velocity, double dot means acceleration. So z is proportional to that acceleration in that case. So how would you relate it? Let me show you how would you relate it, because we know that sinusoidal displacement like a sine omega t, correct? What is y dot? A omega cosine omega t. What is y double dot? It is minus a omega square sine omega t. But if you consider amplitude, the maximum value of y double dot is equal to minus a omega square. So I can plug in this y double dot like minus a omega square. So can I write down like this? Minus minus cancels out. So a omega square over omega n square. I can write down like this. So this is um, the final answer for this one. So you can say that at high like at low frequency forcing frequency, this instrument behaves like a accelerometer. So let's see if we have some. Yeah, one more important concept is the displacement transmissibility. I want to reiterate that you will be given a quiz, and before the quiz, I'm very hopeful that I'm still grading some of the exams, that you will get the grades back before the quiz. And the quiz will be covering only chapter 4 from problem number from 1 to 30. I think I emailed you. Did you check your email? And it was Saturday. So, so what is displacement transmissibility? So let me show you if you have this system here. So suppose that the transmissibility is an important concept in vibration. Suppose this is our a car, okay, and in this car you have this car can be modeled like this is a bumpy road, like this is my y displacement, correct? And the car, you are sitting over here, and the passenger sitting is like having their own vibration x. Okay, I would say this vibrating at x. So the passenger is vibrating by um, the freedom or degree of freedom by x. So what is the displacement transmissibility ratio? This is we are interested in. And you might see some at low frequency when the car is speeding like maybe 20 miles per hour, the frequency of vibrate the displacement might be higher, but at a high frequency the displacement might be lower. So this, how would you find exact value of this the transmissibility? We call, there are two types of transmissibilities. One is the displacement, the other one is the force. Because you are in the car, you are always under the force from the road to the chassis, and chassis to your car, to your body. So let me show you the the equation of motion. This is similar to what I just showed you here, that it is almost similar. This base is by exciting, and the mass over here is having a different degree of freedom. The total instrument is the net deflection. And similarly over here you will see the base is exciting at y displacement, and the mass system is exciting at different displacement. So this is the total force here, and this can be modeled as like this over here. So we are interested in output displacement, which is our like if it is a car, then my whole body is vibrating at an amplitude x. If you do the math from, take the Laplace transform of this differential equation of motion, you should get this answer. This is the displacement transmissibility. And if you replace s by j omega or iota omega, because we want to see the frequency response, right now it is Laplace domain. So you will find out the frequency response. I'm sorry, this is I omega c. I want to write down equation which is for our interest, the magnitude and the angle. So you don't need to derive this one, but you should understand that what is the concept of displacement transmissibility. And if you take us, this one is the magnitude ratio. I would say transmissibility magnitudes, and this is the angle p, where x is the displacement amplitude of the steady state response, and y is the forcing function, which has the amplitude big Y. So these are the two formulae for the displacement force transmissibility. How would you find out the force transmissibility? So let's go to the. I will solve some problems in a bit. I want to cover this section, but it's about to finish. So let me show you the force transmissibility forcing function here. You will see the only difference between the displacement and force is r square times x over y. So let me show you. This is the so this is now the transmitted force. Like if you are a passenger, the transmitted force, and this is the coming from the road, bumpy road. If it is a car, it can be some other case like a washer and excitation. So it can be different applications, but so you see, what is this? This is the displacement transmissibility. You just multiply by r square, you get ft over fy, transmitted force over the excitation force. You see, this is the forced transmissibility. And if I do the math here, what is fy equals to? Fy equals to k times y. Agreed? So this y is coming over here. So transmitted force can also be written like this: r square k times the amplitude of the transmitted um, force, the displacement, the steady state. As you know that this is the amplitude of the output response. So please note down this formula. The transmitted force equals to r squared times k times the output amplitude. I want to share with you the table formula. So this is important that you solve the problems using, you might solve a lot of problems using this table. So you see, we just proved that this is equal to this. This is a transmissibility for displacement transmissibility. Let us solve one problem. The zero point 0.5 kilogram, zero point 0.5 kilogram mass is shown in the figure, is attached to the frame with a stiffness. So the stiffness value, neglect the spring weight and that any damping. So that's good that no damping, and the mass of spring is negligibly small compared to the mass, hanging mass. The frame oscillates vertically with an amplitude of 4 millimeter. So imagine this is the amplitude of 4 millimeter. I would say 4 millimeter at a frequency of 3. It's hertz. So when you see it is just hertz, so you will use this. I will say you will use this F. So compute the steady state amplitude of the motion of mass. Now, if I go to this formula, so what do you suggest? Do you think I should use start from the displacement transmissibility formula, right? So let's start from the, we have to find out this x. So let me write down this over here. So x over y. Let's start from here. I want to show you, over here. Output displacement divided by input displacement. This is equal to 1. Zeta over here, that means zeta equals to 0. Agreed? And 1 minus r squared whole square plus this is also equal to 0. Agreed? So what is y x? So let me rewrite here 1, it is 4 and 1 over 1 minus r square. Now, how will you find out r square? R square equals to omega over omega n square. So what is omega? Omega equals to 2 pi f, 6 pi radians per second. Agreed? This is the applied force, applied frequency. Okay. And the natural frequency is what? Square root k over m. Square root k. K is 500. M is 0.5. Can you find out r square and or what is omega n? Can you find out omega? Open your calculators and help your professor.
10 square root 10.
10 square root 10. So what is r square, guys? So this, if you do the math, you should get, let's plug it in over here. So r square can be found. I need one decimal, two decimal places answer. Or let's find out what is r square. Yes, r square. In the end, let me try to find it for you. Okay, over here, this is 6 pi. 6 times pi. This is 18.8, and this one is square root 500 divided by 0.5. This is 31. So if you do the math here, 18 18.85 divided by 31.62, 0.596. Agreed? So let's use this formula and you will help me. What is x? The output response, amplitude of the output response. What is that equals to? One student says 6.2 millimeter. Do you agree with him?
Yes.
Okay, this is a complete answer. So you see, the question becomes very easy if you apply the formula. So you will practice at home. This is a homework problem, but it's okay if we solve during the lecture to learn the how to solve these problems. So let's do another problem. Problem number 10. A certain vibration instrument. So let us see the instrument. Vibration instrument looks like this figure, but I want to copy this one for your help. That this looks like this. instrument, and the output response, just to grab this one, and this is the output response. Okay, now let's read the question here. Let me copy it here. A certain vibration instrument like the shown in figure over here. Is this close? Are you guys able to see the screen? I heard some sound, some. Can you guys hear me?
Yes.
Okay. Can you guys see the screen?
Yep.
Okay, let's see the displacement input is given. So input, like from here, this is given sinusoidally. It's a sinusoidal function. The amplitude is here, sine 236 times t. This is omega, okay? This is omega radians per second. Like is, I would say it's very, very fast. People are leaving, I think. Okay, the instrument, the mass is zero point 0.1 kilogram. For what range the spring constant can be assumed to measure the displacement amplitude? So it acts like a vibrometer. When you see the instrument behave like a vibrometer, so what is the displacement amplitude? A. So we have now, guys, we can see that if R is greater or equal to 3, this behaves like a vibrometer. The voltage reads exact net deflection of the transmitted displacement and the mass inside the instrument. It's like accelerometers and vibrometer. So how would you do it? So you will see if R is equal to 3. So this, what is R equals to? Omega over omega n. Agreed? Omega is 236. Omega in square root k over m. That is equals to 3. Now what is missing? Point 1. This is point 1. So it's one equation, one unknown. So can you find out k from here? Or let's do one easy way. Let me show you easy way. From here, R equals to omega over omega n. The easy way is to find out omega n from here. Omega over 3, 236 over 3. 78. So this is 78. So omega n equals to 78.67 radians per second, which is equal to square root k over m. So can I find out k like this? M equals to point 0.1. Okay, guys, what is stiffness value? Is it 6,191? Yes, almost. Yes, it's different. It's okay. One decimal place is not a big difference. Am I doing something wrong here? 78 point. Let me check one more time. Point 1 times. Oh, yeah, yeah. I'm sorry, this should be 619. Have you guys understood? Almost 690. Let's say this is almost 690. Okay, now find out what is the for what is the stiffness value now when it behaves like an accelerometer. So what should be the R value for accelerometer? It should be equals to or less than zero point 0.5. Agreed? So we know that for the instrument like behave like a accelerometer, R should be equal or less than zero point 0.5. Let's assume this is R omega over omega n equals to zero point 0.5, and omega is given, and you can find out omega n from here, 236 over zero point 0.5, which is equal to 472. You agree with me? And from here k equals to, I will say let's keep it inequality to be more accurate. Okay, k would be equal to m omega n square. Okay, should be greater than or equal to. And can you solve for this? So 472, I would say zero point 0.1 times 472 square. If you solve for this, k is larger than 2.228 into 10 to the 4. So you see, larger k means the natural frequency is very small. And that is the case for instrument. Have you understood this question? Let's do another problem. This system, this mass spring damper system is driven by the base excitation. This is the base exciting at degree of freedom, amplitude of y, and this big Y, okay? And derive the expression for the displacement and the steady, this is the amplitude of the steady state. So x equal to x times sine omega t. So this is the expression. So you have to find out what is the expression for that one. So let's do this math here. So this is the equation of for free body diagram. Okay. So this is a free body diagram. All the forces on the left hand side.
Why are we leaving out Y in the spring?
Because the other end is rigidly fixed. Usually if it is not fixed, then we have to take the net deflection.
Okay, yes, you're
And now guys, we have to find out the transmissibility, displacement transmissibility. And from here, if you do the Laplace transform, it is because the transfer function is in terms of Laplace transform. But let me do one more step here. All the x variables on one side and the y variable on the other side. So if you take the Laplace transform, and then you find out this is in the S domain. Okay, I just did not write down S, but this is for sure, this is S domain, the big letters. So you are left with Cs over ms square plus Cs plus k. Agreed. Now you replace s by iota omega because we want to find out the transmissibility in the frequency domain to see at what frequency, what is the bandwidth and what is the Bode plot. So we have to replace up until here. Is this clear? It's the same method. First, you derive the equation of motion, take the Laplace transform, replace s by iota omega, and then find out the Bode plot or whatever you can do to find out. So if you do the math here, so you should be like c iota omega over minus m omega square plus minus m omega square plus c omega c iota omega plus k. Now you just tweak a little bit. So what you have to do here, you can take the square root k over m here. So I will say if you do the math here, it's when you go home, you can do this. This should be the answer. R iota. And what is the, this is in terms of complex number. Do you know, do you know that you can take the magnitude of complex numbers by taking the scale? By the way, the numerator is 2 zeta r. Agreed? Because the magnitude of ith, the imaginary component square, is the same magnitude as 2 zeta r. Agreed? And the denominator is, this is imaginary component, this is the real component. So I would say 1 minus r square, take the square of this component, then imaginary component, and take the square root of the whole. This is the magnitude formula for the denominator separately than from the numerator. Agree? This is your answer. So if you want to find, this is our answer in terms of for the displacement transmissibility. We usually write down in the sub like x over y, but it's not that important. Then it says find out the transmitted force from the base to the mass. So transmitted force to support. So how would you remember that transmitted force equals to k times x. So you just multiply by k with this value. 2 zeta r k. Did I forget one thing here? I forgot y over here. No, I did not. This x over y. So this is a transmission. So x can be, this is a whole x, so can be written like this, divided by times y. So you remember this transmissibility is x over y. So over here it is just x. So the y is in cross multiply to the right hand side, and k is multiplied by the with the x. Have you understood this problem? I'm going to stop the lecture, and I will suggest you practice home at home. Okay. Thank you.